Imagine stepping into the hot aisle of a modern artificial intelligence data center.
Oh, yeah, it is an experience.
Right. Like the first thing that hits you isn't even the heat, though. I mean, it is absolutely sweltering in there.
Yeah, it's like an oven.
Exactly. But it's the sheer deafening volume.
Mm.
It sounds like you're standing on the tarmac right behind a 747 with its engines just spooling up.
Cooling fans are just screaming.
They really are. And you are surrounded by these rows and rows of jet black server racks. And, a single one of those racks can easily hold $500,000 worth of computing hardware.
Oh, easily. Often more.
Right. And inside those metal cages, you have thousands of processing cores. And they are drawing so much raw electrical power that if the facility's cooling system were to fail for even, say, 15 seconds, the silicon inside those chips would literally begin to melt.
It is a terrifying thermal reality.
It is. So the question we're asking today is, how do you monitor a machine that perpetually lives on the absolute brink of physical self-destruction?
Well, you definitely don't just plug in a screen and look for a little green light.
No, I imagine that's not going to cut it.
Not at all. You need a diagnostic nervous system that is just as complex and honestly just as relentless as the machines that it's watching. You are constantly balancing the raw physics of heat, electrical resistance, and silicon degradation against this insane demand for unprecedented computational speed.
And that physical reality of keeping these machines running is something that you, the listener, almost never hear about when the tech industry talks about AI.
No, it's always high-level software talk.
Right. We hear about large language models or trillion parameter neural networks and all the magic of generative AI.
The flashy stuff.
Exactly, the flashy stuff. But we don't talk about the frantic microsecond by microsecond struggle to keep the underlying hardware from catching fire or quietly corrupting data. So this deep dive is your backstage pass into that exact struggle.
We've got some fascinating materials to go through.
We really do. We are looking at a stack of sources released just this month, March 2026. These are 3 highly technical integration guides from Supermicro for their SuperCloud Composer, or SCC, release 3.12.0.
Yeah, so SuperCloud Composer, just to set the stage, is an infrastructure management software platform.
Okay.
Its primary job is basically to provide a single pane of glass, like a unified dashboard, for data center administrators.
Got it.
But the real story in these sources isn't the dashboard itself, honestly. It's the 3 completely distinct hardware architectures these guides cover. We're looking at AMD GPUs, NVIDIA GPUs via their DCGM system, and the Gaudi 3 AI accelerators from Habana Labs.
And I have to say, looking through these, they are not user manuals for the faint of heart.
No, they are extremely dense.
Like dense engineering documents detailing how to connect 3 rival hardware titans to this single monitoring system. And my initial takeaway, just reading through the command line jargon and the raw system metrics, is that these aren't really just software guides.
What do you mean?
They feel like maintenance logs for 3 completely different designs of spaceships.
Oh, that's a great way to put it.
Right. Because all 3 guides share the exact same mission, which is to extract health, power, and performance data and send it up to SuperCloud Composer. But the paths they force a systems administrator to walk to get there, they couldn't be more different.
The divergence is wild.
It really is. You have one ecosystem demanding you compile monitoring code from scratch using parallel processing threads. Then another is navigating this maze of modern Linux package security. And then a third one bypasses the host operating system almost entirely by dropping a highly privileged container directly onto the bare metal.
And the differences in those deployment mechanisms, they tell a massive underlying story about the competing philosophies in the AI hardware space right now.
Okay, unpack that a bit.
Well, you're seeing the legacy of traditional graphics processing kind of violently colliding with the highly specialized demands of neural network acceleration.
Right, because a GPU was originally built for video games, not AI.
Exactly. But before we explore that friction between AMD, NVIDIA, and Habana Labs, we have to look at the central brain pulling all the strings here.
The SuperCloud Composer.
Right, but SuperCloud Composer doesn't just talk to the hardware directly. It relies on a mastermind architecture built around a tool called Prometheus.
Yes, and the sources map this out beautifully. In the NVIDIA DCGM integration guide, there's this detailed network architecture diagram, and it breaks down the flow of all this telemetry data.
It's a very rigid hierarchy.
Very rigid. Down at the bottom, you have the compute nodes. The diagram labels them host 1 through host 10. These are the $500,000 physical machines holding the actual GPUs, doing the heavy lifting for your AI workloads.
The grunts on the front lines.
Exactly. So let's say host 1 lives at IP address 192.168.11.1A01. On each of these host machines, sitting right next to the massive AI workloads, is a tiny, lightweight piece of software called an exporter.
Yeah, and the exporter is basically a translation layer.
Like an interpreter.
Exactly like an interpreter, because the GPU hardware, it speaks in raw memory addresses, voltage readings, and these really cryptic driver-level hexadecimal codes.
Right. Stuff a normal dashboard wouldn't
Well,
understand.
exactly. So the exporter's only job is to constantly read that raw hardware data and translate it into a standardized, human-readable format that network monitoring tools can actually digest. It takes machine code and formats it into what we call time series metrics.
Okay, so all of those exporters running on host 1, host 2, all the way down the aisle, they funnel their translated metrics up to a central management server.
Right.
And the diagram labels this the M1 server at IP 192.168.11.91. This M1 server runs a Prometheus container alongside Grafana for the actual visual charts.
Which is standard practice.
Right. And then finally, that M1 server packages the broader insights and passes them up via an HTTP API to the SuperCloud Composer Ubuntu virtual machine, which sits at IP 192.168.11.97.
And Prometheus is the critical piece of engineering in the middle of that whole chain.
Tell me more about Prometheus because it comes up a lot.
Yeah, it's an open source systems monitoring toolkit. It was originally built at SoundCloud back in 2012, actually.
Oh, wow. SoundCloud, like the music streaming site.
Yep. And it has since become the absolute industry standard for cloud-native time series data.
So what makes a time series database different from, like, a normal database?
Well, a time series database doesn't work like a standard relational database. It really doesn't care about complex tables of customer names and billing addresses and all that.
Okay.
It is highly, highly optimized for storing basically just two things: a metric name, like GPU temperature, and a timestamp with a corresponding value.
So just GPU temp 12.000 85 degrees.
Exactly. Millions and millions of those pairs, streaming in constantly.
Okay, so if we pull this out of the server rack and put it into a scenario we can all visualize, think of this architecture kind of like the kitchen of a massive, high-stakes Michelin star restaurant.
Okay, I like this.
So the compute host 1 through 10, are the different physical cooking stations. You have the grill, the sauté station, the fryers. And the exporters running on those machines are the individual line cooks. They're the ones physically touching the heat, watching the steaks, monitoring the oil temperature.
And an exporter doesn't care about the whole restaurant. The line cook on the grill only knows about the grill.
Yes, exactly. Now, the M1 server running Prometheus is the expediter standing at the central pass. They aren't cooking a single piece of food themselves. They're just standing there with a master clipboard, tracking every single metric from every single station.
Gathering all the orders.
Right. And then the SuperCloud Composer virtual machine sitting at the top of the chain, that's the restaurant manager sitting in the back office.
Okay.
The manager doesn't need to hear the line cook yell that a specific steak is at 120 degrees. The manager just looks at the expediter's aggregated clipboard to analyze the macroscopic efficiency of the entire kitchen. Like, are we consistently bottlenecking at the fry station every day at 7 p.m.?
Do we need to route more electrical power to that specific zone?
Yeah.
Taking that analogy further, the mechanics of how that expediter, meaning Prometheus, gathers the data is where we uncover a massive architectural decision in these guides.
What do you mean?
So the sources provide screenshots of the Prometheus.iml configuration file, and in that file there are two global configuration settings that dictate the rhythm of the entire data center.
Okay, what are they?
Scrape interval is set to 15s, and evaluation interval is set to 15s.
15s, as in 15 seconds. And that word scrape is heavily loaded in systems administration, right?
Yeah.
It implies a pull model rather than a push model.
Yes, exactly. A push model would be the line cooks constantly shouting at the expediter every time a temperature changes by a fraction of a degree.
Which sounds chaotic.
It would be. In a data center with thousands of GPUs, if you let the hardware push error logs and temperature updates to the M1 server whenever they feel like it, a cascading hardware failure will create a massive broadcast storm.
So if one thing goes wrong, everything screams at once.
Yeah. Right. If one power supply dips, causing 100 GPUs to simultaneously throw power limit warnings, all those push messages would flood the network switches at the exact same millisecond.
Oh, wow. You would effectively DDoS your own monitoring server just when you need it most.
Exactly, you DDoS your own infrastructure. So Prometheus flips the script entirely. It aggressively pulls or scrapes the data. Every 15 seconds, the M1 server knocks on the network port of host 1 and host 2 and asks for the current state.
So the expediter is asking for updates, not just waiting to be yelled at.
Right. It dictates the tempo. No matter how chaotic the compute nodes get, the monitoring traffic remains perfectly predictable.
Well, wait, 15 seconds? In a GPU doing trillions of floating point operations a second, 15 seconds is an absolute eternity.
It really is.
If you think about an AI training run processing thousands of tokens, a GPU could overheat, heavily throttle its own performance, ruin the timing of a parallel workload, and then cool back down before Prometheus even knocks on the door for its next update.
It absolutely could do all of that in 15 seconds. But you are hitting on the classic observer effect in computer science here.
The observer effect, like in physics.
Sort of. Every
Yeah.
time you measure a highly complex system, you use resources, right? CPU cycles, memory bandwidth, network capacity, resources that the system could otherwise use for its actual AI workload.
Ah, right.
If you configure Prometheus to scrape every single millisecond just to catch those microfluctuations, the exporter software running on the host has to constantly interrupt the CPU to gather those hardware metrics.
So you end up spending all your processing power writing down what you're doing instead of actually doing it.
Precisely. And then you have to store it all. The Supermicro guides show the system service file for Prometheus, which includes the flag storage.tsdv.path varlib Prometheus.
Okay, so that's where it saves the data.
Yeah, that defines where the time series database physically writes to the disk. If you pull thousands of metrics from thousands of hosts every millisecond, you will fill hundreds of terabytes of expensive high-speed storage in a matter of hours, just with diagnostic logs.
Which is insane.
Right. So that 15-second scrape interval, it's the industry's golden mean. It provides high enough resolution to chart meaningful thermal trends and catch memory degradation before a catastrophic failure, but it keeps the network and storage overhead low enough that the data center remains profitable.
That makes a lot of sense. So Prometheus is our expediter, dictating this 15-second rhythm. But what happens when the cook it's talking to is an NVIDIA GPU running a massive generative AI model?
It gets complicated.
Because the expediter doesn't just ask, hey, are you hot? It gets handed a massive spreadsheet of microsecond-level trauma.
That's a great way to put it.
Let's look at the specific telemetry NVIDIA passes back, because they are undeniably the dominant force in this space right now. Their integration relies on the DCGM Exporter, which stands for Data Center GPU Manager.
Right. And the prerequisites outlined in the guide for this NVIDIA stack are incredibly rigid. The guide mandates Ubuntu Server 24.04 as the operating system.
Very specific.
It is. It requires the CEDA toolkit version 13.1, and it specifies a strict requirement for Golang version 1.25.5.
Now, I noticed a specific command in the OS setup phase that speaks volumes about modern Linux security. The manual instructs the administrator to deploy CUDA keyring, explicitly stating that the old apt key method is deprecated.
Yeah, that deprecation is a major shift in how Debian-based systems handle software trust.
How did it work before?
Well, historically, when you added a third-party software repository, like NVIDIA servers, you used apt-key to download their public GPG key and add it to your server's global keyring.
And a global keyring sounds like it opens a lot of doors.
Exactly. The problem with a global keyring is that a key added for NVIDIA is suddenly trusted to sign any software package on the system.
Oh, wow.
Yeah. If an attacker compromised the NVIDIA repo, they could theoretically push a malicious update disguised as, say, a core system utility, and your server would blindly install it because the global keyring trusted the signature.
It's like giving the plumber a master key to every room in your house just so they can fix the sink.
Perfect analogy, yes.
So CUDA keyring isolates that trust. It places NVIDIA's key in a dedicated directory, us share keyrings, and modifies the sources list so that the system only trusts that specific key for software coming specifically from the NVIDIA domain.
Right, it's the principle of least privilege applied to software distribution.
And that level of precision seems to extend to the requirement for Golang 1.25.5.
It does. Prometheus itself, and actually almost all of these hardware exporters, are written in Go.
Why Go?
Go was developed at Google specifically for highly concurrent networked applications. It compiles down to a single static binary file, meaning it doesn't rely on a fragile web of shared libraries on the host system.
Okay, so it's robust.
Very. And the specific version requirement, like 1.25.5, usually points to a reliance on highly optimized garbage collection routines or maybe specific networking libraries introduced in that exact release to handle the sheer volume of data that DCGM pushes out.
And the volume of that data is staggering. The guide includes the contents of a file called defaultcounters.csv.
The Rosetta Stone.
It really is. This is the Rosetta Stone for the DCGM Exporter. It lists every single data point the exporter pulls out of the silicon every 15 seconds. And, looking at this CSV reveals a brutal reality about GPU wear and tear.
It's not pretty under the hood.
No. We tend to think of server hardware as static, right? Like it's a piece of metal that's either broken or working. But these metrics show a machine constantly pushing itself to the absolute edge of failure.
The thermal and power violation metrics are the clearest evidence of that.
Yeah, let's talk about those.
The CSV tracks DCGM FIDUP thermal violation, DCGM FIDUP sync boost violation, and DCGM FIDUP sync boost violation, and DCGM FIDUP board limit violation.
There's a lot of violations.
It is. But the crucial detail here is the unit of measurement. The help message in the guide indicates these are measured in microseconds of throttling duration.
Microseconds. The implications of that are profound, aren't they?
Yeah.
It implies that the GPU's firmware has a layer of autonomous self-preservation that is operating far, far faster than the 15-second Prometheus scrape. The AI workload is demanding so much power, trying to push the clock speed so high that the physical silicon hits a thermal ceiling where the electrical resistance threatens to physically damage the chip.
It would literally melt itself if it could.
Right, so the internal governor has to instantly slash the power draw for just a few microseconds, letting the silicon cool by a fraction of a degree before letting the workload ramp back up.
The silicon is practically breathing. It's this continuous microscopic cycle of acceleration and thermal throttling.
It's like a sports car with a speed governor that kicks in every time the engine gets too hot, but happening thousands of times a second.
Exactly. So as a data center engineer monitoring SuperCloud Composer, you aren't waiting for a giant red alarm that says the server overheated and died. You are watching the aggregate microsecond count of those thermal violations creep up over a month.
Ah, so it's a trend line.
Right. If Rack 4 is showing 10 times the thermal violation microseconds as Rack 5, and they are running the exact same workload, you know the physical airflow in that hot aisle is compromised, or maybe the thermal paste on those specific GPUs has degraded. You diagnose the physical world through these digital throttling metrics.
That is fascinating. But the GPUs aren't just fighting heat. They are also fighting the physics of data transmission.
The networking side is just as brutal.
Right, because when you are training a massive language model, the parameters are too large to fit in the memory of a single chip.
Not even close.
So the model is fractured across dozens, sometimes thousands of GPUs, and they have to pass intermediate mathematical results back and forth constantly. The CSV file maps this out under the PCIe and NVLink sections.
So NVLink is NVIDIA's proprietary high-speed interconnect. Standard PCIe lanes route data through the motherboard's central nervous system, right? But that introduces latency.
The bottleneck.
Exactly. NVLink allows GPUs to bypass the motherboard entirely and talk directly to each other's memory at hundreds of gigabytes per second. But pushing that much data across physical copper and silicon at light speed introduces the risk of signal degradation.
Right, and we see that in the metrics. The exporter tracks standard bandwidth, like TX and RX bytes. But then you look closer and see DCG Amfi DVP SAR play counter. And under NVLink, you see CRC flow control errors, CRT data errors, replay errors, and recovery errors.
Yeah, so CRC stands for cyclic redundancy check.
What does that actually do?
When GPU A sends a massive block of tensor calculations to GPU B via NVLink, it attaches a tiny mathematical signature based on the contents of that data. When GPU B receives the payload, it runs the exact same math. If the signatures don't match, the data was corrupted in transit.
But wait, how does data just get corrupted inside a sealed server case? Like nobody's touching the cables.
It's wild, right? It can be electromagnetic interference from the massive power supplies nearby, or microscopic variances in the copper traces on the printed circuit board. And, most unpredictably, single event upsets caused by high-energy subatomic particles.
Wait, really? Like particles from space?
Literally. A cosmic ray, or an atmospheric neutron, can literally strike a microscopic transistor inside the NVLink bridge and flip a 0 to a 1.
That is mind-blowing. So a single cosmic ray hits a server rack, flips one bit of data.
Yeah.
And a replay error just means the receiving GPU caught the bad signature, and it forced the transmitting GPU to resend the data.
Exactly. The application didn't crash, the user never saw a blue screen, but the entire multi-million-dollar supercomputer had to pause for a fraction of a millisecond to repeat itself.
And if you're an end user, think about the last time you prompted an AI like ChatGPT, and it was streaming text back to you beautifully, and then it just hung on a single word for 3 seconds before continuing.
We've all seen that.
Right. And there are network latency reasons for that, of course.
Right.
But at the hardware level, you might literally be waiting for a cluster of GPUs to resolve a massive spike in NVLink replay errors because of a failing cable or a burst of cosmic interference.
The hardware completely hides its pain from the software, but the DCGM exporter logs every single flinch.
Which naturally leads us to the most inevitable metric of all, which is permanent hardware decay.
The ECC metrics.
Yes, the CSVO file devotes an entire section to ECC metrics, and you can see how ECC, or error-correcting code memory, acts as this final line of defense against the physical degradation of the chip.
And the exporter categorizes these memory failures meticulously. It separates them into SBE, single-bit errors, and DBE, double-bit errors.
Okay, single and double.
Right. And it further tracks them as volatile, meaning errors that have occurred since the last system reboot, and aggregate, which is the permanent lifetime tally of errors for that specific physical piece of silicon.
Okay, so a single-bit error is exactly what it sounds like, right? One microscopic capacitor in the VRAM loses its charge unexpectedly, and a single bit flips.
Correct.
Because ECC memory stores redundant parity data alongside the actual workload data, the hardware's memory controller can instantly run a mathematical formula, identify exactly which bit flipped, and just flip it back before the software even knows it happened.
It's seamless.
It's like finding a typo in a book, right?
Yeah.
If you see a sentence that says, "The dog chased the CXT," your brain corrects it to cat without breaking the flow of reading.
That's exactly it. But a double-bit error is when two bits within the same memory word are corrupted simultaneously.
And the math can't fix that.
No. The Hamming code algorithms used in standard ECC can detect that multiple bits are wrong, but there just isn't enough parity data to figure out how to put them back together. To use your analogy, a double-bit error isn't a typo. It's someone spilling dark black ink over the entire word.
Oh, wow. If the system can't read the word, and it hands that corrupted data up to the AI training algorithm, the mathematical weights of the neural network become permanently poisoned.
Yeah, it ruins the training run.
So a double-bit error usually triggers an immediate hard crash of the application to protect data integrity.
It has to. But what's truly fascinating is how the DCGM metrics reveal the hardware's response to these errors over time. Look at the metrics labeled DCGM-fied retired SB, retired BB, and retired pending.
Retired? That sounds ominous.
Oh, there's also uncorrectable remappedros. This is the silicon actively cannibalizing itself to survive.
Cannibalizing itself.
Yeah. If a specific physical sector of the memory chip starts throwing dozens of single-bit errors every day, the GPU firmware realizes that microscopic patch of silicon is physically degrading. It's dying. So, rather than waiting for a double-bit error to eventually happen and crash the system, the hardware permanently retires that memory page. It essentially draws a quarantine zone around those dead cells and tells the operating system's memory manager to never map data to those physical addresses ever again.
And it just uses less memory overall.
Well, enterprise GPUs are manufactured with hidden reserve rows of memory cells that the operating system can't normally see.
Oh, like a spare tire.
Exactly. When a row dies, the firmware seamlessly remaps the logical memory address to one of the physical backup rows.
That is incredible.
And the DCGM exporter is watching this slow, silent decay. When a systems administrator looks at the SuperCloud Composer dashboard and sees the retired pending metric jump, they know the GPU has exhausted its ability to self-heal. It's out of spare tires.
So they will preemptively yank that $500,000 server out of the cluster during the next maintenance window, long before the AI researcher running the workload ever notices a problem.
Exactly. It's an incredible symphony of self-preservation.
It really is.
Yeah.
And the Supermicro documentation shows this monitoring happening across vastly different hardware generations, too.
Yeah, that was an interesting detail.
They provide scrape configuration examples specifically targeting a system named V100 SYS 40209GP-TVRT, right alongside another named L40 SYS 6211C TN12R.
The V100 and the L40.
Right. And the V100 is an aging architecture from 2017, built for early deep learning, while the L40 is the newer Ada Lovelace architecture. So the SuperCloud Composer is acting as this temporal bridge, normalizing the decaying heartbeat of 7-year-old silicon alongside cutting-edge accelerators, and it's funneling it all into the exact same 15-second Prometheus rhythm.
And that unified view is the holy grail for a cloud provider. You want all your hardware speaking the same language to the dashboard.
Right.
But as we move from the dominant force of NVIDIA to their legacy rival AMD, we see exactly how difficult that unified view is to achieve in practice.
Let's talk about AMD, because
Yeah.
that was a very different guide.
Completely different. Because while the end result, dashboard and SuperCloud Composer is the same, the engineering required to integrate AMD's ecosystem reveals a deeply fragmented data center reality.
The AMD integration uses the AMD SMI Prometheus Exporter. SMI stands for System Management Interface. And right away, the operating system requirements diverge completely from what we just saw with NVIDIA.
Night and day.
Where NVIDIA demanded Ubuntu 24.04, the AMD guide strictly requires Ubuntu 22.04.5.
Right, which is an older long-term support, or LTS, release from Canonical. Furthermore, the AMD setup mandates the ROCm stack, which is their equivalent to NVIDIA's CODA, specifically version 6.3.3.
And a different version of Go, right?
Yes, it requires Golang version 1.23.5 as opposed to NVIDIA's 1.25.5.
Now, to a casual listener, this sounds like a minor detail, just a couple of version numbers. But in a massive cloud infrastructure environment, this divergence is an operational nightmare, isn't it?
Oh, it is dependency hell.
Because if you are a massive cloud provider trying to avoid vendor lock-in by purchasing both AMD and NVIDIA server racks, you can't just deploy a single unified operating system image across your floor.
No, you are forced to maintain parallel, highly segregated deployment pipelines. The Linux kernel headers, the shared C libraries, the Python environments, everything behaves slightly differently between Ubuntu 22.04 and 24.0.04.
It's basically two different operating systems.
Pretty much. The fact that the monitoring software itself relies on different versions of the Go compiler means your infrastructure automation tools have to be deeply aware of the physical hardware before they even begin installing software.
And the installation method itself is a total throwback. With NVIDIA, we bypassed the deprecated apt key and downloaded a pre-compiled Debian package. It was essentially plug and play.
Yeah, very core.
But the AMD guide instructs the administrator to literally clone the exporter source code from a GitHub repository and compile it locally on the server. The specific command provided is cd AMD SMI Exporter's src, then make -j64, and then sudo make install.
Yeah, compiling C++ or Go code from source in a production data center environment is generally avoided whenever possible.
Why is that?
Because of that dependency hell I mentioned. If the server is missing a single development library, the compile process fails. But let's look at the specific build command they provided. Make j64.
What does that j64 mean? GUMake is the standard build tool, right?
Right. It reads a make file to figure out which pieces of source code depend on each other, and it feeds them to the compiler. The j flag stands for jobs.
Okay.
It dictates how many parallel execution threads make is allowed to spawn during the compilation process.
Oh, I see.
So by hard-coding j64 into an official integration guide, the Supermicro engineers are making a massive assumption about the scale of the hardware this is running on.
Because 64 threads is a lot.
It's huge.
Yeah.
If you run j64 on a standard quad-core developer laptop, the CPU will spend more time context switching between the 64 threads than it will actually compiling the code, bringing the machine to an unresponsive crawl.
You would just lock up.
Completely. The fact that they casually tell the administrator to spawn 64 parallel compile threads implies that these management nodes are equipped with heavy-duty enterprise processors, likely AMD EPYC CPUs with 128 or 256 threads.
So it's a subtle flex.
It really is. They expect an exporter that might take 20 minutes to compile on a normal machine to be blasted into binary code in a matter of seconds.
The documentation is implicitly acknowledging the sheer horsepower of the environment. But once the binary is finally built, the configuration of the service running it reveals even more about how Linux handles hardware access.
Yeah, this part is really interesting.
The AMD exporter binds to a different network port, 2021, rather than DCGM's 9400. But the crucial step is when the guide adds the current user to specific Linux groups using the command sudo usermod a.render video lore name.
That command dives right into the core philosophy of Unix and Linux, which is that everything is a file.
Everything's a file.
Yep. When you plug an AMD GPU into a motherboard, the Linux kernel creates special device files in the dev directory to represent that physical hardware. Specifically, DevD for the direct rendering infrastructure, and often DevK for compute workloads.
And the POCX file permission system dictates who is allowed to read or write to those device files.
Exactly. Traditionally, the kernel restricts access to the raw graphics hardware to users who are members of the render or video groups. This prevents a random background process from taking over the screen or snooping on the video memory.
So because the AMD SMI Exporter isn't just asking a high-level API for data, because it is polling the raw device files directly to pull out low-level memory timings and power states, it requires the exact same kernel-level permissions that an advanced graphics rendering application would need.
It has to look under the hood, so it needs the mechanics keys.
I love that. The guide also mentions the AMD SMI CLI tool as a bonus for direct command line interaction. This highlights a dual philosophy in administration, doesn't it?
It does.
Like, Prometheus is built for the macroscopic view, the 15-second rhythm feeding the SuperCloud Composer dashboard. But sometimes, when an alert goes off and a single GPU in a massive cluster is misbehaving, a human engineer needs to SSH directly into that specific server, run AMD SMI, and watch the raw power draw fluctuate in real time.
Completely bypassing the Prometheus expediter.
Right. It gives you both the orbital satellite view and the boots-on-the-ground perspective.
And, both NVIDIA and AMD, despite their very different paths involving Debian packages versus source compilation, they both operate within the traditional Linux paradigm.
Right. You install dependencies on the host OS, you run a binary, and it talks to the kernel.
Exactly. But the data center workloads are evolving. Generative AI doesn't always need the legacy graphics pipelines built into traditional GPUs.
Which brings us to the third piece of this puzzle, the AI challenger. The Gaudi 3 accelerator from Habana Labs.
This one is wild.
It is. How does its integration differ from the legacy titans?
Well, if AMD and NVIDIA represented different packaging methods, the Gaudi 3 guide represents a complete destruction of the traditional deployment paradigm. It is entirely built around Docker containerization.
Yeah, unlike the previous guides, there is no mention of installing Golang. There's no downloading CUDA toolkits. No make Najix J64 source compilation, and no agonizing over whether you are running Ubuntu 22.04 or 24.04.
It just doesn't care.
The Gaudi 3 guide achieves the exact same monitoring objective with a single, massive Docker run command. It pulls a pre-configured image directly from vault.habana.ai, sets up its own network namespace, and binds to port 41611.
And containerization fundamentally isolates an application from the host operating system.
That's the whole point of Docker, right?
Exactly. A Docker container packages the exporter software alongside the exact versions of every C library, Python interpreter, or configuration file it needs into a single immutable image.
So it brings all its own luggage.
Right. When you run it, the host kernel uses features called namespaces and Cree groups to create a sandboxed reality for that process. As far as the Gaudi 3 exporter knows, it is the only software running on a pristine machine.
So if AMD is building a custom engine from scratch, and NVIDIA is bolting aftermarket parts onto the chassis, the Gaudi 3 approach is basically dropping a fully sealed, pre-tuned engine block right into the vehicle.
That is exactly what it's doing. The host operating system doesn't need to know anything about dependencies. It just needs to know how to run Docker.
However, a monitoring exporter creates a massive paradox for containerization, doesn't it?
A huge paradox.
Because the entire point of a Docker sandbox is isolation. You don't want a compromised web server container to be able to read the host hard drive or view the memory of other processes. But an exporter's sole purpose is to measure the physical reality of the host machine.
It has to break out of the sandbox.
That paradox explains the specific flags used in the Docker command provided in the guide. It uses the flag privileged and a volume mount defined as -v dev.dev.
Yeah, and in an enterprise security environment, the privilege flag is usually a massive red flag.
Why is that?
It tells the Docker daemon to strip away almost all of the kite group resource limits and namespace isolation, giving the container root-level capabilities over the host kernel.
Oh, so it just hands over the keys to the kingdom.
Pretty much. It allows the container to insert kernel modules, manipulate network routing tables, and directly interact with physical hardware.
And that -v dev.dev volume mount explicitly punches a hole through the container wall. Just like we saw with the AMD render groups, Linux maps physical hardware to files in the dev directory.
Right.
So by mounting the host's entire dev directory over the container's dev directory, the exporter software inside the sandbox can reach out and touch the bare metal device files representing the Gaudi chips.
Going back to your car analogy, You've dropped a sealed engine block into the car, but you've drilled a massive hole through the side of the block so the diagnostic wires can actually reach the pistons.
Perfect, yes. It is a necessary compromise to gain the deployment speed of Docker without losing the low-level hardware access required by SuperCloud Composer.
The Gaudi 3 guide also includes this fascinating appendix detailing the firmware upgrade ritual for these accelerators.
Oh yeah, the ritual, it really reads like one.
It requires manually removing 4 specific kernel modules before flashing the firmware. The command is a chained execution. It goes sudo modprobe hr habalabs, and then sudo modprobe hr habanalabsin, and habanalabsib, and habanalapsin.
All strung together.
Right, and once those are unloaded, you run the HLFW loader, and then you must reload all 4 modules back in.
So the modprobe command in Linux adds or removes loadable kernel modules, which are essentially drivers that extend the kernel's capabilities.
Right.
But the naming convention of these 4 modules reveals the highly compartmentalized hardware architecture of a modern AI accelerator. The chip isn't just a single calculating brain. It's a localized network of distinct utility districts.
Let's deduce what these districts actually are based on the names.
Okay, let's do it.
The base Habana Labs module is clearly the core compute driver. That manages the actual tensor processing cores.
The math engines.
Right. Then the CN module stands for compute networking. Because an AI chip has dozens of distinct processing clusters on a single die, it needs an internal networking protocol just to move data between its own internal cores efficiently.
Wow, so it has its own internal internet.
Essentially, yes. Then the IBE module represents InfiniBand.
What makes InfiniBand different from regular Ethernet?
While traditional servers use standard Ethernet for network traffic, Ethernet's TCP/IP stack introduces far too much software overhead and latency for AI training. InfiniBand uses an architecture called Remote Direct Memory Access, or RDMA.
Direct memory access.
Right. It allows one Gaudi 3 chip in server rack A to write data directly into the memory of a Gaudi 3 chip in server rack B, completely bypassing the CPU and operating system of both machines.
Oh, so the CPUs aren't even involved in the conversation.
Exactly. It forms the ultra-high-speed superhighway connecting thousands of chips together.
And finally, the N module represents standard Ethernet, handling the traditional traffic like the Prometheus scrapes we've been discussing all along.
Right.
So to safely update the underlying firmware of the chip, you can't just run an installer and hit next. You have to systematically unhook the chip from the operating system. You shut down the core compute driver, tear down the internal processing network, sever the InfiniBand superhighway, and disconnect the local Ethernet roads.
You're basically putting the chip into a coma.
Exactly. Once the chip is completely isolated and dead to the OS, the HLFW loader flashes the new brain into the silicon.
And then you boot those subsystems back up one by one. But the documentation explicitly requires verifying the update using the command HL-SMI-L grep SPI.
Right, and using grep SPI is the ultimate verification. SPI stands for Serial Peripheral Interface. It's a very simple, low-level synchronous serial communication protocol used in embedded systems to talk directly to components like flash memory chips.
The lowest level possible.
Yes. They aren't just asking a high-level software API if the update worked. They are using the hardware management tool to reach past the OS, past the kernel modules, all the way down to the physical SPI flash memory chip soldered onto the Gaudi board to verify the binary checksum of the new firmware.
It perfectly encapsulates the entire journey we've taken through these sources. We started by looking at high-level HTTP APIs and JSON payloads, feeding a centralized dashboard in a virtual machine, and we end up physically verifying the actual bits written to a microscopic flash memory chip on the bare metal.
Which brings us to the ultimate synthesis of these 3 integration guides. Like, why does understanding the distinct paths of AMD, NVIDIA, and Habana Labs actually matter?
It matters a lot.
It does. Because whether you are a cloud architect building the next massive LLM training cluster or a financial institution optimizing risk analysis algorithms, your success relies entirely on these invisible telemetry architectures. SuperCloud Composer isn't just a dashboard. It's a universal translator.
Taking all those chaotic dialects and making sense of them.
Exactly. It takes the deeply technical idiosyncratic dialects of AMD's ROCm, NVIDIA's DCGM, and Habana's containerized architecture and translates all that microsecond-level chaos into a single, legible pane of glass for human operators.
It creates a unified theory of data center health out of a deeply fragmented hardware reality.
So the next time you sit at your computer, prompt an AI and watch a flawless, complex answer stream back to you in seconds, I want you to picture the violent physical reality making that possible.
It's a war zone in there.
It is. Picture the thermal limits of the silicon being pushed so hard that the hardware governor slaps the power down for a few microseconds. Picture the ECC memory controller silently retiring its own dying radioactive cells to prevent a total system crash.
Picture the cosmic rays.
Yes, the cosmic rays forcing InfiniBand networks to replay corrupted tensor mathematics. And picture Prometheus standing above it all, relentlessly scraping that telemetry every 15 seconds to keep the multi-million-dollar symphony playing in tune.
It's an ecosystem of staggering complexity, and it's completely hidden behind a simple chat interface.
But I want to leave you with a final thought to mull over, pointing to where this exact technology is heading next. Right now, as these 2026 integration guides prove, we are using highly advanced tools like Prometheus and SuperCloud Composer to gather incredibly dense, high-resolution metrics.
Right.
But we're still gathering them so that a human administrator can look at a Grafana dashboard and make a decision to replace a node or throttle a workload.
We are still relying on human reaction time to manage microsecond-level hardware degradation.
Exactly. But look at the richness of the data flowing through these exporters, the persistent historical tracking of memory decay, the precise mapping of thermal boundaries. With AI models becoming increasingly capable of complex reasoning, how long until the AI itself is plugged directly into the SuperCloud Composer API?
Oh, wow. Closing the loop.
Imagine a data center where there are no human administrators watching dashboards. The AI uses its own hardware performance metrics to predict its own physical failures. It senses the thermal paste degrading on rack 4. It watches the retired pending memory rows spike on its specific NVIDIA L40 towns, and it autonomously, proactively migrates its own thoughts and workloads to a healthier server rack across the building, long before the hardware ever fails.
The AI playing doctor on itself.
Exactly. The
Right.
spaceships won't just generate maintenance logs, they will read them and repair themselves in flight.